Hi there. So my name is Chloe Stanton. I just finished my first year of grad school at Penn State University. But today I'm going to talk about a project that I did here at Georgia Tech with Jen Glass as an undergrad. I actually just finished this project and we literally just got the reviews back from the authors like yesterday, and I'm not even that upset, so I'm kind of like in a good mood right now. I'm sorry, I know a lot of you guys have heard this spiel already many times before, but you're going to hear it again. So I'd like to set the stage first by talking about luminosity and early Earth and how we perceive climate to have changed throughout Earth's history. So early Earth experienced what we call the faint young sun paradox, and that is because luminosity was much dimmer in early Earth history. So if I have the timeline here on the x-axis, well, that's the x-axis, is the timeline of Earth's history. And on these y-axes, I have temperature and solar luminosity. This changes throughout time in a way that we can perceive with these relationships here. So the bold line here is just luminosity increasing through time, and this translates to temperature also increasing through time. The bottom line here is the effective temperature of the Earth and how it would increase if there was no greenhouse effect on Earth. TS represents the line with a modern greenhouse atmosphere, what temperature we would expect throughout Earth's history. Now we have a problem because early life evolved during the Archean at some point. I'm not going to say a number. And the problem that we see here is even with a modern greenhouse, we weren't reaching the point of liquid water due to low luminosity on Earth. So we have a paradox here, and there have been some proposed solutions to this paradox, namely greenhouse atmospheres. First proposed was carbon dioxide and then methane, but today I'd like to spend the time talking about nitrous oxide as a potential mediator for this effect. So in order to talk about nitrous oxide, I'd like to focus specifically on the Proterozoic because it has a very interesting redox environment. Again, the timeline of Earth's history, but now these y-axes are related to the oxygen content of Earth's atmosphere. The Proterozoic is boxed off here, and oxygen is shown to be increased at least to some degree during this period in Earth's history. However, the oceans were hypothesized to remain relatively anoxic and thus were very iron-rich prior to this Neoproterozoic oxidation that we heard about earlier today. So this is important for one particular reason. Nitrous oxide photodissociates at very low oxygen content because there is no ozone shield to protect nitrous oxide from photolysis. So when we're talking about nitrous oxide in early Earth, it's important that we have some kind of oxygen protection to protect nitrous oxide from breaking apart. So we've proposed a new model for the Proterozoic nitrogen cycle. And we have a background here of 0.1 to 0.001 to 0.1 PAL oxygen in the atmosphere. And we have micromolar to low millimolar iron in the oceans, and these are just drawn from the literature. In this regime, I have also an axis for the nitrogen-oxygen state, oxidation state for these species. Again, this is just the photolysis here in the atmosphere that you can have at low oxygen first. Nitrous oxide will be broken down to nitrogen gas. However, Ava Stukin, during her time at University of Washington, hypothesized that NIF had evolved by this time in Earth's history. So nitrogen fixation could have been important during this time. Also, others have proposed that the aerobic nitrogen cycle had also been kicking to some degree during this time in Earth's history as well, producing a bunch of different bioavailable intermediates for the nitrogen cycle. These species all could have translated down through circulation into anoxic waters that covered most of Earth's ocean. And these could have been removed back to nitrogen gas through anammox or through a more familiar denitrification, involving several different intermediates. Now, an interesting feature of denitrification during the Proterozoic is that we had low copper concentrations in the Proterozoic ocean, which may have limited this last step in denitrification, inhibiting conversion of nitrous oxide to nitrogen gas. I'd like to focus on this talk, though, specifically for an abiotic form of denitrification called chemodenitrification. This is a subsequent translation of these nitrogen intermediates back to nitrous oxide gas using different metals. Today I'd like to focus just on iron though, and just on this last step. So for this project, I set out to document the rate of this reaction, shown here, shown to be thermodynamically favorable in modern conditions. And I set out to determine the exact variables involved in the rate law documenting nitrous oxide production as a function of each variable in this equation here. The way I did this was I set out with an anoxic chamber, incubated sterile anoxic seawater with variable amounts of iron 2 and synthetic nitric oxide. I removed the headspace from these bottles regularly and measured the nitrous oxide produced over time using gas chromatography. Some of the data from these experiments is shown here. So with single substrates, you only see very little, very minimal nitrous oxide on the y-axis produced over time on the x-axis. However, if we start increasing the reactant concentration, holding nitric oxide constant here, you see increased nitrous oxide production as we increase iron concentrations as well. Then holding iron constant, you see the same effect if you increase nitric oxide concentrations as well. This translates back to the rate law by plotting in a special way. So here I've gotten two plots just pulled from this same data, color coordinated. If I plot the log of the initial reactant concentration on the x-axis and on the y-axis the log of the initial rate, I see a linear relationship shown here. And the slopes of these relationships corresponds to the order of reaction with respect to each of these reactants. And then I can plug in to this rate law that I derived here. The pH was found to be constant throughout these reactions, so I dropped the proton, and then I can solve for this reactant constant K here, and we have a complete rate law for this reaction. So this is important for a couple reasons, because we can determine essentially a theoretical nitrous oxide production rate in any environment, but we have to understand things about the reactant concentrations first. So we understand a bit about iron in modern and ancient environments. So in modern OMZs, or oxygen minimum zones, you see very minimal iron concentrations, but there have been modeling studies shown that Proterozoic iron concentrations could have been up to 10 millimolar or even more based on certain studies. Nitric oxide is a little bit harder to constrain. It's actually not commonly measured, even in the modern. But we do see picomolar to nanomolar levels in modern environments, so we translate that to equivalent low nanomolar levels in the Proterozoic. So what does this mean for the nitrous oxide flux? Currently our flux is around 17 teragrams per year, and this translates to a mixing ratio of about 300 ppb in the atmosphere. And I set out using these reactant concentrations to think about what this meant for the Proterozoic in different environments. So I used this rate law in tandem with a couple assumptions. First of all, we assumed that there was a 10-meter thick chemocline in Proterozoic oceans in which chemodenitrification occurred, and that this ocean covered 70% of Earth's surface. And then we capped things with the nitrogen fixation rate. So the nitrogen fixation rate in the modern environment is 100 to 200 teragrams of nitrogen per year. And we assumed that all of this fixed nitrogen in the Proterozoic would convert to N2O through chemodenitrification. So using our rate law, we've made this figure here. So we have the nitric oxide concentration, the first reactant on the y-axis, then iron, the second reactant on the x-axis, and then the contours represent the flux of N2O that you can get out using our rate law. The dashed lines represent this nitrogen fixation rate of 100 to 200 teragrams. And given these dashed lines, we would assume that this could happen in environments with low nanomolar NO and low millimolar iron, which we think could have been possible in the Proterozoic based on our previous studies. So this is cool. Now we know how fast the N2O was being made, but how much and what did that mean for the climate in the Proterozoic. So we set out to do some photochemical modeling. So this is a complex figure, but all we have here on the x-axis is that flux out from our kinetic model. And then on the y-axis, we have the atmospheric concentration of N2O, how much actually is retained in the atmosphere. And this changes as a function of oxygen due to that photolysis. And that point there represents our current modern state, but we targeted, depending on the oxygen concentration that you think was present during the Proterozoic, this regime for how much N2O and how much flux of N2O we could have during the Proterozoic. Pumping this into a climate model that was previously completed by Roberson et al., we wanted to see how much this would translate in terms of temperature and warming during the Proterozoic. So here, this figure, before I put any lines on it, I'd like to just talk about it a little bit. On the x-axis, we have the mixing ratio of N2O, which translates to the y-axis on this first figure. On the x-axis, or on the y-axis on the second figure, we have surface temperature in Kelvin as a result from this climate model. And all lines on this plot are going to correspond to a background near-modern greenhouse of carbon dioxide and methane. And here I've just kind of bookended a couple important values that we think could have been possible as a minimum and a maximum for potential Proterozoic nitrous oxide concentrations in the atmosphere. And what this means in terms of temperature depends on when in the Proterozoic we're speaking about, because the Proterozoic is a really long time. So in the early Proterozoic, luminosity was much lower, so we experienced lower surface temperatures. In the late Proterozoic, it was higher, so this relationship between the N2O mixing ratio and temperature changed throughout this time period. But during this time period, with a background N2O of 0.1 to 5 ppm, which we could expect given our assumptions and our modeling calculations, we do see a significant level of warming just from nitrous oxide. So just to conclude and wrap up, the climate modeling that we've done assumes that we can get up to 5 degrees of warming from nitrous oxide just from chemodenitrification. But we have built in a couple assumptions into these calculations that I think have a little bit of wiggle room, and I think it's really exciting to start thinking about how this affects the rest of the ancient nitrogen cycle, and in turn how further ancient nitrogen cycle studies could affect chemodenitrification. For example, we don't have very good constraints on ancient nitric oxide concentrations. Could have been much higher considering the ocean was primarily anoxic. Also, if ancient nitrogen fixation was faster than it is today, this is a possibility. This would also change our calculations. In the same sense, if it was slower, this would change our calculations as well. Also, it is likely that not all of this fixed nitrogen engages in chemodenitrification. So we presented one end member here. Conversely, there's another end member in which no nitrogen is chemodenitrified. Also, there are interesting caveats that we've only recently kind of thought about in terms of feedbacks with ancient oxygen. In high oxygen environments, nitrous oxide is broken down into nitric oxide, which engages in ozone breakdown. So there would be a feedback in which ozone protection would be scavenged even in high oxygen environments. So I'm really excited about this project. I'm excited it's my first submitted paper, so I'm glad it's done. So, if you guys have any questions, just let me know, and I'd like to thank my old lab group. It's good to see everybody, and some of our funding sources as well.
All right, questions for Chloe. Ooh, yeah.
So I'm just curious, what is the sink of N2O in your model, and how long was the residence time of N2O in your model?
Yeah, so that would be the photolysis. Just as soon as you release N2O into the atmosphere, you're breaking it down into nitrogen gas here. Oh, there we go.
So you considered it in your model, like?
Yes,
Yeah.
that's.
And
yes.
how long was the lifetime? Like,
It's very rapid, but it depends on the oxygen concentration.
yeah, that's why I'm asking.
Mm-hmm.
Yeah.
So, I mean, if you look, going back all the way. Yeah, so if you look here, it depends greatly on how much oxygen you have.
So your residence time is changing with the concentration of oxygen.
Yes.
Okay, yeah.
Hi, thanks for the great talk. I was curious, you had mentioned, I forget exactly which reaction it was, but metal limitation in a Proterozoic ocean potentially changing the rates of some of these biological processes. And so I had a question specifically for nitrogen fixation because I guess presumably the Proterozoic ocean was also molybdenum limited, and so maybe that might have affected the rates of nitrogen fixation. So I was wondering what your thoughts were.
So I think all of these, I kind of just put them in really small font on purpose, kind of, because some of these studies are a little bit skeptical in my eyes. But if you look here, Ava Stukin did this paper studying nitrogen fixation enzymes, and she's particularly interested in alternative cofactors besides molybdenum and how that could have pertained to ancient enzymes in the nitrogen cycle. So this one paper in particular hinges the entire nitrogen fixation crux on something else besides molybdenum is engaging this reaction. So whether or not that's true, I don't know. I think there is definitely some isotope evidence that they're kind of hinging their argument upon there. But I think, again, today we see mostly a molybdenum cofactor, and I think that's something that we need to think about when we talk orders of magnitude like this.
Thank you.
Other questions?
Yeah.
Could you go back to rate graph, please? Rate.
Which here?
Yes. So I know this is just a general chemistry question. Could you please remind me why you should get the linear behavior for?
So this is assuming first order kinetics for each of these reactants. So there's a little bit of wiggle room here, but this is essentially just kinetic models that you can run for different orders of reaction for each reactant. And this is the one in which gives us a linear relationship. So this is the one that we use. So depending on how linear your data is determining how you plot your data.
Okay. But you got the different order for these reactants, right?
These are called pseudo first order because they're not zeroth order and they're not second order, but they don't fall along the theoretical first order kinetics, which almost nothing does. But this is as close as you're going to get in the real world. I don't know, does that answer your question? Okay.
All right. Any other questions for Chloe? All right, if not, let's thank her again.